And so you can use this microphone. It's less, there is perimeter. There are arrows left and right.
So hello everyone, my name is Matusz and this is my team. This is Ilya, Jaroslav and Dima. And for our final project we decided to tackle a challenge of tissue segmentation from microscopic images. For a start, I have important warning for you. If it didn't work. No.
Should work. No.
Yeah. So this is our message, which kind of steal from Dima. So rocket science is for kids, but bioinformatics is for real scientists. So we decided to kind of keep the legacy of Dima Fishman alive, and we decided to try tackle some problem from bioinformatics to see if it is really so cool as he presented to us. So
you always need to check whether it's turned on.
Sorry. Yeah, so our main motivation for such a task is that creating a model which will automate tissue segmentation from microscopic images. So it can be very useful for various researchers, mainly for purposes to improve speed of the finding of the cures for a disease ranging from rare diseases to common colds. And it can be very useful for researchers for all over the world, which has to tackle a big volume of tissues and microscopy images, and they can kind of explore various effects of various treatments to these tissues in high resolution and really quickly. But obviously this challenge comes with various problems. Mainly it is data shortage. Then there is just limited amount of models you can choose from. And in the end you have to use special metrics for evaluation.
We are working with medical images, in particular microscopy images of tissues, which we have had to segment from the background. The usual problem in this domain is related to the small dataset due to the privacy, etc. So in our project, we as well there was 35 images, and at once we decided to split it into 20 images and 8 validation images. The second usual problem is related to the unbalanced classes. So in our case, there was about 15% of tissues, and the rest of that is the background. Our approach to tackle this is related to the specific metrics, which you will see later, different from accuracy. And also, furthermore, the images were of different sizes, tissues was of different shape, color, and there was general holes and noise and such different problems. So we decided to have two strategies to enlarge our dataset and make it more diverse. The first strategy is called turn-time augmentation. In each step on every image, we got a random crop of size 256, and we had really many different transformations. As you can see, these transformations are really hot, but the tissues, the main idea that the tissues are still distinguishable. Yes, about the second strategy, Dima will tell.
So we tried another approach for make our dataset bigger, which named divide and conquer. So we generated from each original picture 3,000 of small patches, 64 by 64, by uniform distribution, to save the distribution of background and tissue like an original image. And after that, we applied LvDS documentation for these small patches. We used only 5 filters rotate, flipping, elastic transform, Gaussian noise, and channel shuffle. This is examples of filters. We applied for each patch 5 different filters from. So we get from each patch 5 different images, and then after the implementation we can go to the models.
So in semantic segmentation task, we need to use encoder to understand what object we need to segment. After that, we need to use decoder to know where is this object in our image. The first model that we use is Ternau's net, which used pre-trained BDG11 encoder. The second model is UNet. And in train details, we have our vanilla UNet hyperparameters. We use standard stochastic gradient descent as optimizer, 64 batch size, learning rate 0.001, 6 augmentations, and 50 epochs. And in another model, Ternau's net, we use Adam optimizer to about 200 epochs, 10 augmentations, and batch size 16. So we train our model in GPU, and learning time is 4 hours. Okay, and the final train part, we split image into the same 64 by 64 patches, and after that we add in some patches black padding. We use this patch as input of our network, and after that, finally, we glean together these patches and get original output prediction image.
So how did we actually evaluate our models? So usually the metric which is quite widely used in object detection and object segmentation is called IOU, or intersection over union, or Jaggard index. But for better comparability with all other models, we decided to use also precision and recall. So this is our baseline model, which was kind of already better than all the previous models which were trying this dataset. We reached a recall of 9.91 and precision of 0.87. But you can still see, for example, in the picture in the top right corner, that we are not so good at predicting, especially this picture, and we got like 54 recall, and also there were some errors where our network detected just dust or watermarks. So then after various iterations and various trainings, we arrived to the final model, which is a UNet model, which Ilya described. But we were able to get to precision of 0.94 and recall of 0.93. We can see improved results on the picture in the top right corner. All other pictures had quite very good results. And also there was slight improvement in the picture here, but there's still some dust and water we should treat in the future. So here is a quick bar plot to see the differences. So you can only see this is the baseline model, this is the final model, and mainly on the picture 4 and 5, you can see our misclassified ratio kind of changed considerably to the final model. So what are our plans for future? We mainly would like to kind of try to find solution for this water and dust region, which still network sometimes classified as tissues. We get some ideas about oversampling such regions in the training samples. Also, we like to do more hyperparameter tuning in different preprocessing methods and different implementations. And we also got in touch with researchers from US, which are authors of this new emerging architecture, Net++, and they kind of offered help to us, so we may collaborate with them in the future. And to conclude, I would like to kind of address the question from the beginning. So if bioinformatics is really so cool, we obviously have a really small sample to say, but it is a really interesting field and offers really interesting problems which are really domain specific as far as data goes. So we at least learned something. You can check our presentation, you can scan this QR code, and this is all from us. Thank you for attention.
Thank you guys, and it's my pleasure to start giving you these certificates. So Yaroslava Watchman, let's give a round